Recording in progress.
All right. Well, hello, everyone.
Okay, and I hand it back.
Thank you. So let's finish this example from last chapter before we move to the new chapter, which today we're going to talk about damping. This example, I'm not sure if you had a chance to take a look. Washing machine, ideally, when we put the clothes and everything, we wish that the center of mass of everything to be at the center of rotation. Let's say the drum, the clothes and everything to be at the center of rotation. However, we are not that lucky, and the center of gravity of everything is going to be in some distance, which this question call it E. And the drum is rotating with a constant speed. That constant speed, the question set is omega. Not to confuse with the small omega, we show it with this capital omega. So we are curious to find the vibration of the whole system. All right. So this drum by itself, it has a mass m. And remember that the total mass, and the machine without the drum and clothes has also capital mass m. So if you put this washing machine with the clothes in it on a weight, so the total mass is m plus n. Something total mass is m plus n. Sometime in question, they say that, for example, the drum mass is included in this capital M. Sometimes like this one, they are separate. Okay, so let's use Lagrange method for this one. I guess we have used Euler or Newton enough. Let's just use Lagrange as a practice. So for Lagrange, we need two things. We need T and we need U. T, and then we need U. All right. So U is the potential energy. Here we have only springs because we know due to the weight already there is some pre-compression in the spring. So the only things that I need to be worried, and usually we show it by capital U. It is half of K x squared. So that's easy. Remember, I have half of K here, half of K there, so sum will be K. T, remember we said we have three scenarios when something is pure rotation, right? Second scenario when something is pure translation, and the third scenario is a hybrid case or combination of these two. We have here the scenario number 3. We have a rotating pins, it's rotating, but at the same time, this rotating, whatever you want to call it, drum, it is inside a box that box moves ups and down. So we have combination of two. Just to remind you, somewhere on the corner here, we said when we have a mass and it has a center of gravity G, and this mass, let's say, rotate with omega and also move with a velocity of v. So rotate and move. Its kinetic energy has two terms: half of I bar, the mass moment of inertia about g omega squared, plus half of m vg squared, right? So it has to be the velocity of that center. So for this one t, as I said, we have rotation. So I'm gonna need then the first term, half of I bar omega squared, right? That's one thing. So let me move that things a little bit there. So we have the whole mass, the mass m, which is pure translation. So I add that one, half of m x dot squared. This is for the washing machine frame, because remember it has a mass m and it's moving ups and down with the vector that we call it x. That part is easy. Now we are trying to find for the rotating things. As I said, it has two terms, and then plus the second term, half of m vg squared, right? The center of mass velocity for this drum. So how can we find the center of mass velocity? I need your attention for a moment. So we know that this center of mass, if I go inside this machine, it has a velocity going to that direction because I have an omega, and that velocity will be e omega. Right? Everybody agrees on that? We are going to have e omega over here. All right? That's one velocity. If I go inside this machine and I look at this disk, but we know the whole thing is moving with a velocity of x dot. So I need to have another velocity here. I don't know the amplitude or the direction, but let's assume, based on what we assumed here, x, our direction, is going up there. So then I need an x dot over there. So if I stay outside this machine, if I look at the point G, this point G then has a velocity going up, right? And also has a rotation velocity, which is e omega. So then the total velocity of this one is combination of these two, Vg. All right, this is what we are looking after, finding Vg. This combination of these two. When we have two vectors and we have the angle between them, you know what to do, right? It's the angle between them. If this is theta, it's going to be theta. Then the total Vg will be, we can use the cosine formula, right? Vg squared will be x dot squared e omega squared plus 2x dot e omega cosine theta. Okay. So if you forget the cosine rule, whenever we have two vectors, we have the angle between them, we can find the sum of them. And that's a standard formula. The first vector squared, the second vector squared, plus 2 times these two vectors multiply by each other and multiply by cosine, the angle between them. That's the cosine rule. So it means our velocity is then if I want to draw it, like the total velocity will be a vector which is like that vector. So this is VG, the total velocity of this system. So I can put it here, then my kinetic energy will be half of m x dot, half of I bar omega squared plus half of m and Vg squared, which is x dot E omega squared 2x dot E omega cosine theta. Now I regret, maybe we should have solved it with the Euler law. But anyway, that's a good practice. Okay, so we have T and we have U. So this is T and this is U. And we know that the rest is just taking derivatives, right? Let's remove those things down there. So this is our T. So the derivative for Lagrange equation, we know how it works. It is d over dt, derivative of t with respect to our variable here is x dot, right? Plus derivative of u with respect to x. We don't have any external load here, so the other side will be 0. Then it should be u. Okay, let's quickly do the derivative. Derivative of u, t with respect to x dot. So with respect to x dot, I'm gonna have mx dot. I don't have x dot over there. Then I'm going to have another mx dot here. And what else? Plus 2e omega cosine theta. That's correct? Yeah. Sorry, say again? Already a squared, right? Yeah. Relative t with respect to, for Vg, yes, it's already a square. Okay. This is, oops, squared, and we have one here. Okay, so that's that one. Now let's take the derivative of these things with time. What it gives me is m plus m x double dot, right? With respect to time, now I have to deal with minus 2 e omega sine theta multiplied by theta dot. Okay, so theta dot, let's over here deal with that theta dot things. So theta, because this drum is rotating with constant speed, is equal to omega t. That's a rotation speed, right? Whenever you have a constant rotation speed, theta, we can write omega t. Then if you forget, if you move back one slide, we discuss it here that when you have a constant speed and you have a rotation, theta, the position will be omega t. Okay, so moving back here, I have these things there. I can replace it. Let's see what will happen. Gives me m and x double dot minus 2e omega squared sine omega t. Right? Because theta dot will be omega. That's the speed. Yes. Right? Sorry. Oh, half m, right? Yeah, you're right. We have an m here. Thanks. So there is an m which you forget because they multiply by m, but we have a half, like a half. So let's simplify it. It's going to be m. Then this will be m, right? And this will be m. You're right. Thank you. We have an m here which multiplied by the whole things. Okay, so this is that term, and then the last term, derivative of u with respect to x, which is kx. We put all of these things together, so we would get m plus m x double dot plus kx plus goes to the other side, so it becomes me omega squared sine omega t. Something you need to be careful because some student ask, this cosine theta, we only replace it with theta or with 1 when theta is very small, right? In range of 1 degree. But when we are dealing with question of rotation, this theta is not small. It's like 2 pi. The whole thing is rotating 2 pi, right? So we cannot replace it. Remember that sine theta and cosine theta, we are allowed to change them, to approximate them when they are in a range of 1 degree or 2 degrees. Here, your theta is a complete rotation. Something's wrong with this microphone, I believe, right? It's okay? Yeah. So this is our final equation. Later, we may try with the Euler's equation, and you should get to the same equation as we have. Remember, always our standard formula when we solve a problem, we wish to get to this final form. Mx double dot plus kx is equal to f0 sine or cosine omega t. This is our standard form. Like this is the standard form. And we know the steady state response that we are interested is x sine omega t. Like this one and this one, they have to match. If that is cosine, this one is also cosine. And x has a standard formula is f0 divided by k 1 minus omega n squared. I'm just repeating it because I received like few emails before exam. So this is always the standard formula and the standard solution. It is just that with different problems, the forms of this f0 and m and k, they are changing. And soon you will see the new term will be added. So for example, here, this is our f0. This is our omega. This is our stiffness. And the whole things here is our mass. Okay, the mass of the system, the stiffness of the system, amplitude of the force, and the frequency of the force. These are the terminology we use. If I substitute them, I would get xt. Xt then will be f0, which is me omega squared divided by k, and 1 minus omega n squared. Omega n, you know, it's going to be k over m plus n. And this is sine, our omega is omega t. So that's the steady state response that we are interested in, steady state. Now, if some question they may ask, we want the full solution. If the question asks we want the full solution, then xt has the steady state response. Usually we show it by like xp, okay? So it is that xpt plus 2 more terms, a cosine omega nt plus b sine omega nt. Again, some mistake from some of you when you send me email. These new terms, it has omega n, different frequency. Remember we said when a system vibrates, we have two different frequency. They're combining together and makes the whole vibration. One is the frequency, which is the forcing frequency, omega, another one is the natural frequency. And this makes our complementary solution, right? Which we call it XCT. But we said this part is not really that important because when you turn on your washing machine, maybe it takes only a couple of seconds, 3-4 seconds, gone, because soon you will see we are going to add damping to the system, making system more realistic. And this is why we will see for the rest of semester, we care only about the particular solution and not really dealing that much with that part. It is there, but it's small, sometimes maybe big, but it is temporary, it is transient, short. In control, though, like courses in control, that transient is more important than a steady state, because in control, we like to control the beginning, right? The steady state is going to continue forever. So that's our response. We can plot it. I put something on canvas, which I asked to plot this response for different omega. If quickly we do that. So just I want your attention for a few seconds. So this is the response of this system. Yeah. So X is omega, the rotation speed, and Y is the machine vibration, XT that we found. All right. So as you saw it before, it start from 0. Remember, for rotating system, start from 0, goes to infinity at some omega when resonance happen, and then it comes down, eventually gets to 1, right? Now, this is the frequency response, all right? This is the response based on omega. There is no time here. That's the general response of this system. Now, let's say I'm interested in only in omega equal to 100. And by the way, on x-axis, I just showed omega, not omega divided by omega n. I didn't divide it because maybe we are interested to know how our machine is performing. If I run this system at omega equal to 100, I expect to see the amplitude of 2 millimeters. All right. So that's the time response. Omega 100, the amplitude will be 2. This 2, in fact, is this number. There's my pen. So the whole thing's, right, which we call it x become 2 at omega equal 100 RPM. Right? And if I just write the equation, then the equation will be xt2 sine 100t. If I plot it, so I would get this response. Okay? So this is the response of the system, the time response of the system, time x, and the amplitude is 2 millimeters, and it continues forever until we turn off the machine. And frequency of this vibration is 100, like if you count the number of cycles and so on, 100 RPM. Or to be exact, you need to be careful about something else here. This is RPM, right? So this is then has to be 100 multiplied by 2 pi over 60t. Remember over here, always this one has to be in radian per second. So let's run the same system at omega equal to 200. Again, I want your attention here. Let's see at 200, right? If I look at my graph, I expect the amplitude to be 2. So I would say x will become 2 at omega equal to 200 RPM. And we are getting the whole things from like this X from this formula. Or better from that formula. We substitute the values and we get that numbers. So we have that one. All right, so xt this time will be 2 sine 200 2 pi 60 t. And if I run my MATLAB code, so this one has to be 200. And run. So again, see, when I change omega, this graph obviously is still the same because it is for the range of omega from 0 to 1000. But this is my response. It is like the amplitude is 2. You see the frequency change. It is a higher frequency. It is almost double. But I'll let you try this MATLAB code later with different omega and see how it looks like. Or any question? Yes.
Yeah, there's a small omega term.
That's right. Oh, this one, right? Oh, all right. This has to be, thank you. This is omega. Oh, please correct that one. Has to be omega. Anyway, play with these numbers and that MATLAB code. And this is a good example. I intentionally use Lagrange. So you see how it turns out. You may try later with Euler. With Euler, remember that you have like this center, you have the joint force OX and OY. Let's call it O. You take the derivative about that point and then the rest, which you know how to do it. Okay, so let's move to the new topic, which is damping. Give you a minute to take notes, so whatever you do, move to this new topic. So damping or like damper or system with damping, the term, the correct terminology is dampers, or outside people call it shock absorbers, is a mechanism to remove vibration or slow down vibration, because we, as you recall in the first session, we said we try to reduce vibration. In a very simple, let's say, mechanism, if I want to explain it, this damping, most likely even in maybe some new toys, they have this damping, these new small cars. But underneath of your car, if you take a look, you will see like this shock absorber or a damper that we call it. And if we open it up, it is basically a cylinder. Let's say a cylinder like that. And inside this cylinder, there is this piston. This piston can move ups and down easily. Right? That's just a schematic. And then the whole things inside is filled with oil. Now, if I want to push it down, obviously I cannot, right? Because I cannot compress oil. So what then we do is we make some holes like here on this piston. So if I draw a better picture or the top view, this piston is going to have some little hole in it. Okay. Those little holes. Now, when I try to push it down, of course, oil try to come out here and a little comes out there, and the whole thing moves ups and down. That's the mechanism of a damper, and it slows down the motion. Because it is oil, it creates some viscosity, and because of these orifices or these holes there, it creates some sort of pressure, and we are not free to move it easily ups and down. So that's a simple, very, let's say, basic mechanism for a damper. Of course, it involves more details. For example, some maybe O-rings on the side and other details, but that's the whole story. People can control how, for now, let's call it a stiff, or strong. How strong a damping is by just controlling the size of these holes. So you can visualize if these holes are like the diameter is 0, so almost the damping is infinity. You cannot push it down or do anything with it, right? The bigger this hole are, it is easily you can move it ups and down. And we associate with each damping something which we call it damping coefficient. And that damping coefficient depends on those little holes. One of my jobs in the past, when I was designing a shock absorber for a car, was figuring out what should be a right damping coefficient for a car, and then after that translating it to the size of or the number of these holes. And this is particularly if you ask somebody who works, let's say, in a car manufacturer, and they are responsible for designing dampings, they say, okay, we'll try to find this damping coefficient, and we try to then, based on this damping coefficient and some experimental tests, figure out what should be the number of these holes and the diameter of those holes. And obviously, a car without these dampings, they are not going to perform well. Right? You can imagine a car without any damping, so it's going to vibrate forever. We need something to remove vibration and slow down things. Remember those graphs that I showed you? So the vibration is going to continue forever, which we don't like. Like if we excite something, after a while, the vibration goes away. Okay, so that's damping. Our objective here is to now make the model that we have been dealing with so far, make them closer to reality. We add damping because damping can be in different forms. This is something that intentionally we built, and we call it a viscous damping. But air resistance, for example, is damping. Friction is damping as well. But for now, we'll focus on viscous damping. And our objective again here is to model this system. Now, the second part is modeling. So we know how to model a spring. Simply, you know, if this mass M, if I push it to the right by X, then the spring simply create a force, which is Kx. Right? That's a spring that we know how it works. Also, we know that force is not depending on speed, right? No matter how fast or how slow I move this mass. Always we look at the end result. We say the force is K multiplied by X. Damping, which we show it like schematically, like that's a cylinder and piston with this shape. And the coefficient for damping, we show it by C. Somebody decided to show it by C. We call it damping coefficient. So the force that the damping creates depends on velocity, not the amount that I deflect it. Right? So I can have a damping. I can slowly open it up and then don't move it, then it's not going to give me any force. It only depends on velocity v, and the force that it creates is going to be in the opposite of velocity. Always damping, because it is friction, it is in the opposite of the velocity. And what is the value of damping? As we show it here, this force is C multiplied by V, velocity. Okay. So that's the modeling that we use for damping. Similar to spring, if you recall, for a spring, we said we do a little bit of linearization, and we say because it is vibration, motions are small, so we can approximate like a spring as a linear force, Fx. The same with damping. So for a damping, now here, instead of x, I will have x dot, right? X dot is my velocity. Velocity is equal to x dot. And this graph is not a line, it's more like a curve, like that. But we approximate it because we are dealing with a small range of motion. We can approximate it by a line and write down F is equal to Cx dot. This is for a spring, and this is for damper. Okay, so with that, now let's also deal with something else, and that's Rayleigh dissipation function. Rayleigh is a scientist, probably you've heard his name. I guess he was a professor in Cambridge University. Anyway, so he's in math, in many fields, also in vibrations. That's the same Rayleigh. So he found a function which shows the amount of energy that is gonna be wasted or dissipated by damping. That function, again, we're not gonna go through the proof where it comes from, but if you're interested, just Google Rayleigh's dissipation function. It's a very long proof. That's the amount of energy that is gonna be, let's say, dissipated for a damping. Okay? So we know, like for a spring, the energy is in a form of potential energy. It is half of kx squared. So there is a similarity here. Half of c v squared. E is the velocity, right? And for mass, you know the amount of energy that it generates or it gets is half of m x dot squared. For damping, the energy is half of c x dot squared. Right? So now we get to the Lagrange equation. We know the Lagrange equation before damping. Now that we add a new term, damping, our Lagrange equation will get this long, ugly form that I'll explain it to you in a moment. So the Lagrange equation, Q is our variable. Why do we have Qi? Because this Lagrange equation is for general system. You can have many variables. For example, a 2-degree freedom system or 10-degree freedom system, you can still use the Lagrange equation. We will see it when we get to the n degree of freedom system. But for now, we have just one variable, let's say x. So this Lagrange equation, so for a SDOF system, a single degree of freedom system, either we have x or theta, right? Our variable. So this becomes d over dt derivative of t with respect to x dot minus derivative of t with respect to x, derivative of u with respect to x, and derivative of r, we have a new term, which is for the damping, with respect to x dot. Be careful, this is x dot velocity is equal to the force in the direction of x, all right, Fx, which we show it by Q. This is the force, the external force, remember, the external force in direction of x. This force can be also a moment, a couple, so mx, if our system is a rotating system. For example, if I'm writing things with respect to theta. I guess one of your tutorial was a rotating system. Or maybe in future also in one of your tutorial, you will see for a rotating system. So anyway, that's the function that we use. It has one variable, but this function can repeat itself. For example, if I have a system with 10 variables, so I'm going to have 10 Lagrange equations. Okay, any question for this one? Are we good? Let's solve one problem with Lagrange and Newton and see how the equation will turn out. So we'll start with the easy one with the Newton law, because again, here we have just a particle. With the Newton law, what we need to do is, obviously, we start with a free body diagram, right? Let's do that one. So we start with the free body diagram. I have the mass m, and so I'm going to have two forces here. This is kx, this is cx dot. And this is the variable that we decided. Remember, this x is up to us. We can show it in any direction that we want. But depends on that, we will show these kx and cx dot, the direction of those. So you probably notice that I don't typically draw the weight, because if we want to really do a complete job, we need to draw the weight and also put this external load there as well, right? But we don't need those, and we don't show them because we only care about the direction x. So it is okay in your exam or in your assignment or wherever you do, like solving the problem, just show the forces in x direction. You don't need to draw mg, and because in this problem we need to draw mg, right? Because there is no tension, pre-tension or pre-compression in a spring. We need to draw it, but the reason that we don't, because we know that we don't care about that direction. We only care about this x direction. So the Newton law simply says sum of the forces is equal to ma, mass and acceleration. My forces minus kx, because it is an opposite of x, so minus kx minus cx dot is equal to m. My acceleration here is x double dot. So mx double dot cx dot plus kx equal to 0. And this is our standard form from now on. So before we didn't have, bless you, we didn't have cx dot, but now we have a new term, cx dot in our equation. And it's going to be our standard form. Remember from the title of this chapter, we are in free vibration. So, and this side will be 0. But next chapter, there's going to be a force there. We're going to do this exactly similar things that as we did before, but just we are going to add a new term, which is c to our equation. And again, no matter what is the mechanism, the shape of the structure that we are dealing, we're going to end up with this equation. We are going to call this coefficient system mass. It may not have the unit mass. You saw in some example, it is, for example, ml squared or something else. this is going to be the damping coefficient. And this is going to be the system stiffness. And they can have any unit, anything, but the constant value, they are not changing. Now let's solve the same problem with Lagrange equation, okay? So Lagrange equation, I know that I need T and U. So T, simply here I have just one mass, it is mx dot squared, and U potential energy is half of k x squared. So I know my Lagrange equation, it is d over dt, derivative of t with respect to x dot, plus, or first it was minus, derivative of t with respect to x, derivative of u with respect to x, I almost forgot, and then it is 0. Oh, we have r, right? Plus derivative of r with respect to x dot is equal to 0 because we don't have any external force. So let's quickly find them. Derivative of t with respect to x dot, it is mx dot. When you take the derivative, be careful. You are taking the derivative with this variable, x dot, right? There is no t. Our variable is x dot, and I'm taking the derivative with respect to that variable. So it is mx dot. Obviously, when I do the time, I would get mx double dot. This term is 0. In most of problems that we will solve, t with respect to x is 0. But there are problems that this term is not 0. Usually when things are not linear or in rotating system, you will see we are going to have. But most of the cases, there is no x in t. Derivative of u with respect to x, kx. And you see now we need a new term, which is r. And r is half of c x dot squared. The Rayleigh's dissipation function. Right? And that's why we show it by r, because of his name. Okay, maybe in future I should invent a function. It's going to be m dissipation function. So, and r with respect to x dot. Again, remember this is x dot, our variable is x dot. Simply it becomes cx dot. If you put them together, we will get mx double dot plus cx dot plus kx equal to 0. The same equation. So both methods are valid in your exams, or when in future you solve problems, you can use either of these two. There are sometimes, depends on the problem, there are advantages in using one of these solutions, but sometimes no, maybe it's just a personal choice. And there is no rule when which one is better. But usually when drawing free body diagrams is going to be messy, we try to get to these Lagrange equation. All right, so far, are we good? Okay. So from now on, then this is the equation that we are going to see a lot. And first, we need to make a standard form out of it. That's the next topic, because you will see working with this one is not easy. It's a second order differential equation, and we are going to solve it and then use it similar to what we did before. Which, rather than starting it, I prefer to wait until Friday. And on Friday, we will continue with that one. Try not to miss Friday's session. Thank you very much, and have a good day.